Okay, so now let's go and work into some polynomials that have a binomial raised to a power, but then also we have the k. And so this is something we're familiar with, is regarded as the vertex form, and we kind of spent some time as far as the transformations of the functions when we were looking into basic transformations, previously in our functions unit. So, but now we just want to kind of elaborate a little bit more as far as finding the y-intercepts, finding the zeros, and the transformations. Now, notice I didn't talk about multiplicity here, and the reason being is because these functions are not in, or these polynomials are not in factored form. You can see, remember, factored form is when you have a product. Your terms or expressions are separated by multiplication. So we do not have that in this case. So when we're going to be finding our zeros, our real zeros in this case, we're just going to be able to find, it's basically just going to be the x-intercept. But remember that the power of each of these zeros, now I kept this kind of simple here, that the power is they're going to be, there's maximum total of 2 zeros or maximum total of 3 zeros. But the multiplicity is not going to take, is not going to help in this case. We're not going to have a repeated zero. So when we look at the graphs, which I forgot to add here, so what I'm going to do is I'll take these and I'll make sure I add them in Desmos, so therefore you can view them on the worksheet. So therefore you can kind of see that all of these are going to cross, cross at their x-intercept, and there's not going to be any repetition with them as well. So it'd be kind of something interesting for us to be able to kind of see what is actually going on with that multiplicity, and as well as where those other zeros can come from, which we'll talk about later. So let's just kind of focus on this. I did want to break this up into, identifying the y-intercepts, identifying the zeros, the transformation. So let's go and just get right into it. This is a quadratic, something you should hopefully be familiar with. If we're trying to find the y-intercepts, again, we're just trying to find when the y values when x is equal to 0. So I am just going to replace 0 for x. Okay. And you can see here 0 plus 2 is 2. 2 squared is 4. 4 minus 0 is 0. So in this case, my y-intercept is at 0. So it looks like this graph crosses exactly at the origin. Now to find the zeros, we're basically, that's looking at when y or f of x, you can replace this with function notation, is set equal to 0. So we're going to set this our function equal to 0.
Can someone please call the main office? We have the schedule.
So we have,
Whoever has the schedule, can you please call the main office?
okay, so we have here, just going to plot in x plus 2 and then squared minus 4. Now here's where I really wanted to get into, because again, we got to make sure, this is different than the previous example where we just needed to apply the, inverse kind of root method. Here we can't undo the square root until we've gotten rid of the subtraction. So in this case, what I'm going to need to do is I'm going to add a 4 to both sides. And therefore I have 4 equals x plus 2 squared. Now I can introduce the square root method. So I take the square root of both sides. And now here's the important thing, where last time we were taking the, the root of 0, it didn't really matter because it's always going to be 0 and there's no plus or minus. Well, now I'm taking the square root of 4, so I have to introduce plus or minus 2 equals x plus 2. And I don't really need the parentheses anymore because I got rid of the square root. So now, when I subtract to find my zeros, here comes the interesting case. X equals negative 2 plus or minus 2. Now, this comes back. Now, this is interesting because you notice when we were talking about multiplicity in the last example, we were saying, hey, it's, you're 1, 0, but it's like repeated, right? Well, here, we can't, this is not in factored form, so that is not the multiplicity of that 0 because it only works when that's that only works when it's in the factored form. So now when I go ahead and do this, you can see that I actually have 2 zeros. I have negative 2 plus 0. So I'm going to write this in set notation. So that's going to be 0. And then negative 2 minus 2, which would be negative 4. So I have 2 zeros, which based on the degree of my polynomial makes sense, right? We talked about, the polynomial is going to have the same number or will have a maximum number of real zeros as the degree, and so that works. And then let's go and look at our end behavior. So for this one, you can see that this is a positive. So therefore, then again, I am going to, I can see that this is just going to rise left and rise right. All right. Let me see. Did I do in this one? No, I did not. Okay. All right. Let's go and move on to this example because it's another squared one. So, I kind of like that example. And now in this one, I am going to change this. I am actually going to make this a positive and then this a negative. So really we have the equation y equals a negative x minus 1 squared plus 8. Okay, so the reason why I looked at this because I think my example that's what I provided, so I want to change this because this affects obviously the transformations. As far as identifying the y-intercept, it's not going to make a difference because we're still going to follow the same process. We're going to set 0 in for x and then solve for y. So we'll have y equals negative 0 minus 1 squared plus 8. Okay, so when we do this, we have 0, so minus 1, which is negative 1 squared. Negative 1 squared is going to be positive 1, but then that's a positive 1 times a negative, so that's a negative 1. Negative 1 plus 8 is going to be 7, so y equals 7. Now, when we go ahead and find the real zeros, now in this case, what we're doing is we're, again, setting our function equal to 0 and solving for x. So now, when I go ahead and do this, negative x minus 1 squared plus 8. Okay, so what's important here is before we can solve inside of this binomial, we got to undo all the operations on the outside. So we're going to have to subtract an 8 first. So therefore, we have negative 8 equals negative x minus 1 squared. Okay, now I need to get rid of this negative. That's the last operation on the outside. So therefore, now I have a positive 8 equals negative x minus 1 squared. Now I can use the square root method to take the square root of both sides. And again, we have to use the positive and negative. Remember, you can only take the square root or the even root of a positive number. So if we had a negative, then we would have no real x-intercept or no zeros. So that's important just to kind of clarify that. But in this case, we can take the square root of 8 and just remember a little sidebar here. The square root of 8 can be broken down. So again, that's plus or minus. Remember, the square root of 8 can be broken down into the square root of 4 times 2, which can be broken down into 2 square root of 2. So we always want to simplify things whenever we can. So therefore, I have plus or minus 2 square root of 2 equals now negative x minus 1. Okay, so there's a couple different ways, we can do this. Obviously, we're going to, it doesn't really matter if you're, multiplying everything by a negative. That's just going to like flip those, around. So basically, I'm going to have x equals, if we add a 1 to the other side and then divide by a negative, it's going to turn into a negative 1. So, if I add a 1 here, well, let me just do this real quick. So if I add a 1 to both sides, then I'd have negative x is equal to 1 plus or minus 2 square root of 2. But again, we got to solve for x, so we got to divide by negative 1. So I'm going to take a little space over here. So therefore, let's use it in blue. So therefore, x is equal to negative 1. Now again, it doesn't matter plus or minus because then if you multiply by negative, it's still going to be plus or minus. So that's just going to be plus or minus 2 radical 2. Okay, and there's really nothing else we can do, as far as simplifying this. So we can write this in set notation. I am perfectly fine just leaving it in that form. Don't really need to spend the time breaking them up and writing them separately. So that's perfectly fine with me. If we want to find the transformations, now again, I added a negative on the outside. So again, we got to think about what that's going to do to the function. That is going to reflect the x-axis. We have a negative on the inside, so that's going to reflect the y-axis. And then just remember that the easy way to be able to identify what this transformation is if you factor out that negative. you can see that this is going to be shifting 1 unit to the left. So we just say shift 1 unit left. Okay, so a lot going on there, but you can see here that these both have 2 different zeros. And again, they have those 2 zeros, as you can see, that matches up the degree, which is interesting. When you look at the graph, you can kind of verify those. And also I asked about the end behavior, and you can see that this is negative, that's even, so therefore the graph is going to fall left and fall right. Falls left, falls right. Okay, so now let's go and look at the cubics. So same pretty much process here, looking at the cubic functions. Finding the y-intercept, let's set x equal to 0. So we say y equals 0 minus 3 cubed minus 8. I get negative 3. Negative 3 cubed is going to be a negative 27. So y equals negative 27 minus 8 is going to be a negative 35. Okay, again, you could write that as a coordinate point if you wanted to. 0 comma negative 35 is another way to write that. To find the zeros, again, we're basically just replacing our y or f of x with 0 and then solving for x. So let's go and do that in this case. So 0 equals x minus 3 cubed minus 8. Now, again, kind of the same thing like we did with the cubic functions here. We're just going to use our inverse operation. So the first inverse operation we're going to do here is add an 8 to both sides. All right, and therefore we get 8 equals x minus 3 cubed. Now we need to use the cube root feature on both sides, and it's important that since the cube root is an odd root, we don't need to do the plus or minus. So now we just need to simplify. What is the cube root of 8? Well, the cube root of 8 is actually just 2, because 2 times 2 times 2 equals 8. There we go. So therefore that equals a positive 2 equals x minus 3 plus 3 plus 3, and we have 5 equals x. Now again, this is the interesting thing, because a lot of times people see the 3 and they're like, oh, there's going to be 3 zeros. And guess what? There are 3 zeros. And I don't want to keep on pushing this. We're going to learn about this later. But the interesting thing is, in the last example, there was 3 zeros because it was 1 0 multiplied 3 times. The multiplicity was 3. That's not the case here. We don't have a multiplicity. The multiplicity, well, we would have to look at it in factored form to be able to identify the multiplicity. So right now we don't have an idea of the multiplicity, but it's not the repeated, 3. And so that's just something interesting I just want to bring up. So therefore, when we start to talk about this in the next couple days, you'll kind of start making that connection as far as, where are those zeros? If there's going to be, 3, like what other types of zeros can we have if they're not real? Part C was identify the transformations. Oh, I didn't ask for the end behavior, did I? Well, good. End behavior is just a good practice for us, so I'll continue that. So the transformations here, you can see that's just going to be shifting 3 right and then down 8. Did I not do the transformations over here? I forgot to. Aha. All right, so let's go back over to that. So here it's going to be, we're going to shift right 3 units and down 8 units. Let's go and fix these transformations since I forgot to do that. Well, let's call that D. Let's put C over here. That's going to be shifting left 2, down 4. So we'll do left 2, down 4. All right, back over here, let's identify the end behavior just because keep in sync with everything. You can see that if I was to expand this, my highest degree would be 3. Doesn't really matter. This negative 8 is not going to affect the degree of the polynomial. And my leading coefficient will always be positive. So therefore, it is going to fall left and rise right. All right, let's get on to the last example. So y equals 3x minus 1 cubed plus 1. All right, well, let's get through the same process here. Hopefully you're kind of saying, all right, so to find the y-intercept, you just replace 0 with x. Yes, it's the same thing over and over. It doesn't really matter what we're getting here. So in this case, again, we have a negative 1 cubed is negative 1, negative 1 plus 1 is going to be 0. Cool, so this graph crosses through the origin. Part B, setting your equation or function equal to 0 and solving, or replacing y with 0 and then solving for x. Now here is one where a lot of students get mixed up because they say, uh-oh, you can't take the square root of a negative. And you're right, you can't take the square root of a negative. So thankfully, we're not taking the square root. We're taking the cube root. And you can take the cube root of a negative number. Cube root number, so what multiplied by itself 3 times gives you -1. And that's -1 times -1 times -1. So it works. So the cube root of -1 is -1. Then we have 3x minus 1. Now, if I add a 1, I'm going to get 0. So when I divide by 3, I'll get 0. So x is equal to 0. So that's going to be all of my zeros here. For C, which is going to be the transformations. Let's see here. We're going to be shifting up 1. The best way to be able to identify this transformation is just to set it equal to 0. Add 1 over, so you can say, let's say x is equal to 1/3. So therefore, I'm going to be shifting 1/3 to the right. Or if you like to, which I like to do, you can factor out the 3. And therefore, you can see, oh yeah, it's x minus h. H is 1/3, right? That's the 1/3. So therefore, you're shifting it 1/3 to the right. So 1/3 right. And then also we have that we have a compression, right? We have a horizontal compression here, factor of 3. So we can just say a horizontal compression factor of 3. Then let's go and look at the end behavior. This is going to be odd. That's still going to be positive, so that's going to be odd. So therefore,
Rosa, can you please come to the main office? Rosa, can you please come to the main office?
so therefore, what we'll have here is that's going to be, again, a positive leading coefficient with a odd degree. So therefore, this will fall left and rise right. And let me just make sure, did I go over that in the other examples? Did I do those transformations? I forgot to. Shift 1/2. Yeah, so if you remember back in this one, there is a horizontal compression of factor of 2. So horizontal compression of 2. I got that one. I just forgot that. So I just want to make sure I add that in there. So there you go, ladies and gentlemen. I really wanted to kind of compare what happens when we're dealing with our transformation when it's not in factored form, as well as compared when it is in factored form. And again, we're all to solve this without factoring or anything else. That's kind of like the nice idea about having something that's written as a binomial raised to a power. It can really make a lot of the solving and a lot of the things that we're looking for rather easily. So we don't always have to expand it. Some of our questions might be look for us expanding, but we don't always. We can figure out a lot of information on the graph based on there. And again, I will have the links to the graphs available for you so that you can go ahead and check them out. So now what we need now, the next step that we're going to look into is, well, what about if we're given an equation where we don't have a binomial raised to a power? How do we create that? And that will be coming up next.